Welcome to Chapter 2. So with this chapter, we're going to get started talking about matter. So matter is anything that has mass and takes up space. Okay, so this excludes energy. Energy is something a little bit different. So are you ready for a pun? Because have to? Well, maybe, if it goes. There we go. So this goes back to that famous equation E equals mc squared, where E equals energy, m is matter, and c is the speed of light. So you matter unless you multiply yourself by the speed of light squared. Then you energy. Yeah, these are the science jokes. Alright, so different types of matter. You have elements. So these are the different types of atoms that we were talking about in the last chapter. So there are 118 elements. These are just some examples of ones that you will commonly see. Oftentimes, if it's a pure element, it'll either be just a single atom of that element, or you'll have a bunch of different atoms of the element complexed together or bonded together or something like that. Right? A compound is two or more atoms of different elements bonded together. So that's the key there. It is different elements. So even if you have these 4 phosphorus atoms bonded together, that is still considered an element because they are all phosphorus. Okay, so a compound would be something like water, where you have 2 hydrogen atoms and you have 1 oxygen atom. Okay, so 2 different types of elements. Then a mixture is when you have 2 or more elements or compounds that are mixed together, but they're not chemically bonded. Okay, so these hydrogens are chemically bonded to this oxygen. So this is not considered a mixture, it's considered a compound. A mixture would be something like if you dissolved sugar in water. Okay, the sugar and the water molecules do not chemically bind, they just mix. Okay. And so another terminology here, an atom is the basic unit of matter. Okay, you can actually get what are called subatomic particles. They are usually called quarks. We're not going to go that in depth because when you get smaller than an atom, things get really weird. Okay, but atom, this is a basic depiction of an atom. It's not wholly accurate anymore, as we'll see later on. So this model is probably 40 to 50 years out of date, but well, it's a really good depiction, a simplistic depiction of an atom. So in an atom, okay, you've got a couple different parts. You have your nucleus, we'll go through the different, these subatomic particles actually. So subatomic particles, you have 3 different types. You have protons, neutrons, and electrons. Okay, and then the subatomic particles that make up those are the ones called quarks. Okay, so like I said, it can get kind of weird once you get down to that level. Okay, because quarks, it's called the quantum level, and it's just, yeah, it deals more with energy than it deals with matter. Inside of an atom, you're going to have your protons. So these are the positively charged particles inside of an atom. They actually determine what type of element you have. Okay, so the number of protons determines the element itself. Right? So protons are very important to an atom. It is really the identity of the atom itself. So if you add a proton into the nucleus of an atom, you're going to change what element you have. Okay, then you have neutrons. Neutrons do not have a charge, so they are neutral. They are really just there to kind of help protect all of the positive charge inside the nucleus. Because as we'll learn later on in this class, if you get a lot of like charges together, they tend to push each other out. So that would mean that really most atoms would not be stable. except for the neutron. The neutron kind of separates out those positive charges and allows the nucleus of the atom to kind of stay together. Then you also have electrons. So electrons have a negative charge. These are the kind of freer subatomic particles. They are more on the outside of the atom. They actually take up the most space in the atom, even though they are the smallest particle, just because they have so much room around the nucleus to move. They are the parts of the atom that will get exchanged during chemical reactions, during different chemical bonds, things like that. So they will actually determine the atom's charge. So if you lose an electron, you're losing a negative charge, which means that you get positive. And then if you gain an electron, you're gaining a negative. So you get more negative on the atom. Okay. The nucleus contains just the protons and neutrons. Okay. So if I ever ask what's the charge on the nucleus, okay, you've got positive and neutral. Add those together and you have positive. So the nucleus is positively charged. Most of an atom is empty space, okay, because that's where the electrons move around, but you have a finite number of electrons, so you only have a specific number of them, and they have quite a large space to move around, okay? So basically, if we were going to do this analogy, if you had, I think it's a marble in a football stadium, the marble would be the size of the nucleus, and then the football stadium itself would be roughly the size of the atom. Okay, so those little electrons have all of that space to move around, and they're still a part of the atom. So the atom's size is actually determined by how far the electrons are from the nucleus. Okay, so the nucleus has the most mass of the entire atom, because the electrons don't carry a whole lot of mass, but it's all condensed in a very small area. So there's this one little tiny core in the center of every atom that has the most mass, but then the size is determined by the electrons, the size of the atom itself. Okay. All right, so then when we talk about compounds, compounds have different properties than the elements they contain. Here's an example, okay? We've got, well, this is just an example of a compound. Here we have carbon, which is the C. Okay, so this is how compounds in science are written. Basically, you'll have the letter or the letters, the atomic symbol of your element that will tell you what element you're dealing with. And then you'll have a little number underneath it, okay, that tells you how many of those elements you have. So this is saying we have 16 carbons, we have 10 hydrogens, 2 nitrogens, and 2 oxygens. And because they're written like this with no plus sign in between them, this is one compound. So all 30 of these atoms are bonded together. Not necessarily all to each other, okay, but they're usually just bonded in a line. Okay, so you have 16 carbon atoms, 10 hydrogen, 2 nitrogen, 2 oxygen. Add all of that up together and you get 30 atoms in this one compound. Okay, now this compound, okay, is very different from the elements that make it up. So for an example, carbon, elemental carbon is either graphene, so graphite, diamond, or it can be found as a carbon nanotube, which is kind of a newer form. Elemental hydrogen, nitrogen, and oxygen are found as colorless gases. They are also flammable, so fun stuff there. But C16H10N2O2 is actually the chemical formula for indigo, which is a chemical dye. It's a blue-colored dye. So if you think about basically combining diamond with 3 gases in a very specific proportions, you would get indigo. Okay, so elemental or elements are going to be very different than the compounds. Right? So anytime you have a number coming in front of the chemical formula, Okay, so like you see this 3 here, that is called a coefficient. Okay, it actually shows you the number of molecules of that type. So if you have 3 C16H10N2O2, you actually have 3 indigo molecules. Okay, so that's a little bit of terminology there. All right, so talking about mixtures real quick. So we have pure substances. So in pure substances, you have either an element or a compound, but there is only one substance. So if you had pure water, no matter where you look in that sample, you're only going to find water molecules. Okay. Now, if you have a mixture, you're going to have 2 or more elements or compounds, but they will not be bonded together. Okay. There's no chemical bonding happening between those elements or those compounds in the mixture. And then talking about mixtures, you have 2 different types of mixtures. You have what's known as a homogeneous mixture, so homo meaning same. So homogeneous, evenly mixed, no matter where you look in that solution, you're going to see the same composition. Okay, so it's an even mixture. Basically, think if you mixed sugar into water. Okay, the sugar is going to dissolve. It means that it's basically suspended in the solution, in the water. It's evenly mixed in and dissolved in it, and that forms a homogeneous mixture. Okay, if you are creating steel, okay, that has to be a homogeneous mixture. Otherwise, you're going to have weak patches in the finished product, which is not very good. Not a good idea. Coffee and milk. Okay, so once they're mixed together, because yes, I know it's coffee and it's me and coffee. But once they're mixed together, okay, you don't have coffee, you don't have milk, you have a mixture of the 2. And it's an even mixture. So you're not going to find just a random bubble somewhere in the drink that is just coffee. Okay. Sugar water, like we talked about earlier. And then with heterogeneous, hetero meaning different, heterogeneous mixtures are not evenly mixed. So if you think about orange juice, okay, that has high pulp in it, okay, so you've got all of that pulp, it's mixed into the liquid whenever you shake it up, but over time it'll start to settle back out. Okay, so it settles to the bottom. Now, usually when you see something that says mix before using, okay, mix well before using, it is a heterogeneous mixture. So they want to make sure that you're getting, like, basically the way to ensure that you're getting the same kind of sample from a heterogeneous mixture is to mix it up every time you try to use it. You also get this with like Italian salad dressing. Okay, soup is also another good example because you have your water and then you have all the different things in the soup. Okay, so it's not a heterogeneous mixture, or it's not a homogeneous mixture. Oil and water, they don't like to mix, so they will actually form a very distinct set of layers. Okay, so this is just kind of looking at the breakdown here. So if you have a pure substance, so it's just one compound, one element, okay, it can be split into elements or compounds. Elements, again, just contain atoms of a single type of element. Compounds will have molecules of 2 or more elements bonded together. Mixtures is where you have these different compounds, but they are not bonded together. Okay, so homogeneous mixture, again, is equal mixing. Heterogeneous mixture is kind of a haphazard sort of mixing. Okay? All right, and that is the end of section 1.1.